Morning, everyone. Today, I would like to talk about measuring displacements on the seafloor using a shipboard multibeam sonar. Now, shipboard multibeam is a little bit unique among the suite of tools that are applicable for seafloor geodesy because it insonifies a very wide area on the seafloor when you perform your experiment, unlike alternative methods. Unfortunately, the trade-off is that shipboard sonar is much less accurate than alternative seafloor geodetic measures. In general, most of the literature will quote resolutions of tens of meters depending on the depth of your survey area, and there have been few studies to try and prove that at this time. However, we do believe that if we are only interested in measuring changes on the seafloor rather than the bulk seafloor characteristic itself, then we can do a little bit better than this figure of tens of meters. And we are going to attempt to do so by analyzing multibeam tracks that have been taken at slower than normal ship speeds. So for this study, we shall be comparing two pairs of ship tracks. The first is a pair of multibeam surveys that were taken in 2003 by Dave Chadwell and Dave Sandwell above the Juan de Fuca Ridge. They were collected using a Simrad EM120 multibeam sonar, which was then aboard the research vessel Roger Revelle. These data are freely available on the NGDC website and were taken at a very slow ship speed of 0.8 knots. Now, these tracks are, in addition to being special because they were collected at the slow ship speed, also are separated by about 10 to 30 meters in space. So they are very closely repeated in addition to being slow, and they were taken about a week apart from each other. In addition, the coherence between the tracks is sufficient that not only can we analyze the raw bathymetry data itself, but we also have coherent sidescan data associated with these tracks that we can analyze. The other pair of tracks that we are going to be comparing are some multibeam surveys that were taken above the Cocos Plate in 2001. These were taken also aboard the research vessel Roger Revelle with the same instrumentation as the previous studies, and they were repeated about a month and a half apart at a ship speed of approximately 11 knots. We just so happened to get lucky that the first track was taken as some fellows were going out to do an experiment, and then when they came back in, they returned to port along the same line. These two tracks are separated by about 500 meters in space, which sounds like a lot, but let's remember that the swath width for multibeam tracks at this particular depth is about 10 kilometers, and so there's still plenty of overlap between these surveys. Another nice thing about these particular tracks is that they are about an average depth of 3,000 meters, which is a little deeper than the previous tracks, which had an average depth of approximately 2,300 meters, but the overall difference in depth is not incredibly significant. It's just a small percentage. So all of these surveys are separated by very small increments of time. And so between them, there is no nominal change in the bathymetric signal. However, we can turn this to our advantage by introducing synthetic offsets into one of the grids as we create GMT grid files using these data. And once we have these grid files, we simply perform a digital image correlation scheme in order to try and measure the synthetic offset that we introduce. Thus, we perform a residual analysis in order to say something about the accuracy of displacements that we can measure using these surveys. Before moving on, however, I would like to pose the question whether or not it is fine in order to perform these type of digital image correlation on these data. And so here I have displayed one of the gridded data products from the Juan de Fuca surveys. It is gridded at about a 20 meter by 50 meter spacing, and we can see the bathymetric signal in this plot. In order to answer the question how coherent the tracks are, I have gone ahead and circled three small features that show up on the grid. They are all a few pixels large, and in a short moment I'm going to switch to the sister track of this particular grid, and we can see that in fact those three features are preserved quite nicely. So we are able to track relatively small features between these two grids, and in addition to these three features, much of this fabric on this side of the ridge is also preserved between the two grids. So we should be able to perform a sufficiently good correlation between these two grids. I'd also like to perform the same exercise using the associated sidescan for this survey. The sidescan is more abundant, so we can grid it at a finer resolution. And once again, I have circled three relatively small features that we can compare between the tracks. For those who are confident in their eyesight, I would also encourage you to look at this fabric over here, as well as this linear feature and all of these signals in that particular region, because as I switch to the second grid, you will see that they have all been preserved quite nicely. So it is appropriate for us to try and perform this type of correlation analysis on these surveys, and so we will go ahead and do so using a relatively standard cross-correlation scheme. We perform a normalized cross-correlation on these grids, and then the exercise of finding out what the displacement between them is an exercise of solving for the maxima of the correlation peak. In this case, it was a maximum of 0 meters and 0.5 meters, and so it is very close to the center of the grid. We fit the correlation peak using a simple polynomial and obtain a residual therein. Now, after performing this for a wide array of synthetic offsets, we can obtain both mean and 2 sigma values for the residuals obtained therein. The mean of the residuals we would like to be close to 0, which is the case, and then the 2 sigma values tell us something about the accuracy with which we are able to reproduce these synthetic offsets. And we can see that for the slow Juan de Fuca tracks, we can track the accuracies to a meter or even better than a meter, some fraction. And surprisingly enough, the sidescan data does a better job of tracking displacements than the raw bathymetry does. In comparison to the faster Cocos bathymetry tracks, these displacement measurements are on the order of tens of meters, as is often quoted in the literature. So this is well and good, but perhaps it is a little bit difficult to believe, because this would imply that with a 20 meter by 50 meter grid spacing that we can see displacements of 1/20th to 1/50th of a pixel. And so we would like to try and verify this using an alternative method. Instead of comparing these grids in the spatial domain, we shall do so in the Fourier domain using a multi-taper cross-correlation scheme. And so we measure the cross spectra between the grids, and from the cross spectrum, we are interested primarily in the coherency spectrum, shown here, and the phase spectrum, shown here. Now, both of these are plotted on the same wave number scale, and the important thing to note is that where the coherence is high, we can see a phase ramp in the phase data whose slope is dependent upon the offset between the grids as per the Fourier shift theorem. Where the coherence is low, the phase is essentially random. So in order so that you can more appreciate the actual phase ramp, I will go ahead and remove the random phase data. And we can see that for the same shift of 0 meters and 0.5 meters, there is an appreciable shift that we can see in the phase ramp. All we need to do in order to measure the offset is to fit a plane through this ramp, and we have obtained our measurement therein. Once again, we perform the same type of residual analysis, and the mean and 2 sigma values are shown in this table. Once again, the means are very close to 0, as we would like them to be, and the 2 sigma values for the slow bathymetry tracks are significantly less than a meter, on the order of 1/2 a meter, and the side scan data in the range direction is about 0.3 meters, which is very, very good. Also, once again, the Cocos bathymetry is on the order of tens of meters, and so these are in agreement with the results we obtained before using the spatial cross-correlation. I have gone ahead and taken the liberty of printing both tables out side by side so that you can verify for yourself that these values are in agreement with each other, and so we have obtained sub-meter displacement accuracies using repeated multibeam and side scan tracks using 2 completely independent processing techniques, which is rather exciting. Now, it is perhaps not particularly surprising that the slow bathymetry data is more suitable for these type of analyses than the fast bathymetry data. However, something I would like to bring to note is that the side scan data has a superior accuracy compared to standard multibeam bathymetry. And at these magnitudes, this is more than sufficient to measure co-seismic and post-seismic offsets due to large earthquake events. And so to wrap things up, I've gone ahead and plotted these results on a chart. They are still rather preliminary in that we've really only done this analysis for 2 different ship speeds. There is a wide array of ship speeds in between that we would like to perform similar analyses on, as well as other parameters that we would like to measure, such as the baseline length, seafloor depth, and the bottom characteristics. With that being said, we hope to be able to perform some experiments in the near future exploring these parameters so that we can figure out what the most efficient or optimal strategy for performing these type of repeated multibeam surveys is with regard to these type of analyses. And with that, I will leave it open to questions.
Thank you very much. Are there any questions?
Yes?
So you didn't mention things like sound speed and latency in the system and all the various snakes that go into basket snakes with vertical and horizontal precision. How do you deal with all of that? Tides.
So, for those who are unable to hear, this gentleman was asking about how we deal with uncertainties due to the sound speed of the water column and such. And right now, we have not explicitly taken these uncertainties into account. We hope that having repeated the surveys within a very small time frame, that these contributions are negligible. However, I will acknowledge that internal waves can play a large part when it comes to these things. So that's one of the future parameters that we will need to explore.
Yes, go ahead.
So yeah, you're showing kind of variability in the along track spacing, ship speed here.
Yes, so the Okay, so once again, this gentleman was asking about differences in the along track and cross track variability. We are actually measuring the displacement resolution in both directions In these particular slides, I called the along track resolution the azimuth and the across track resolution the range. This is terminology that mostly stems from satellite radar, but it is still applicable for these type of studies. In particular, the physics governing sidescan data is identical to that governing radar. What was that?
Have you thought about oversampling the cross-track as well?
I have, honestly, I have not.
I have a short question for you.
Sure.
Since it's, there are big differences between actually slow speed and high speed, did you look at the actual road data? Because that's probably where the difference lies in the number of pings you have over the real estate, and analyze that rather than analyzing grid points, process grid points.
All right, so the question there was whether or not we have analyzed the raw data, and the simple answer is that no, we have not. We try to work with as raw data as possible, but the unfortunate truth is that the multibeam sonar itself does quite a bit of processing before even spitting out a data product. The side scan is probably more raw than the bathymetry is with regards to that, though.